recording is on, and all right, here we go. So, hello, hi everyone. Well, thanks for joining us today for this differential equations modeling with MATLAB webinar. My name is Mike Michailidis. I work at MathWorks. I am an applied mathematician, and part of what I do at MathWorks is I work with students and educators to make their teaching and research a little bit more interesting, more exciting using our tools. So today, I want to quick little announcement before we begin with the actual webinar itself. So MathWorks this year, and for the past 3 years or so, has been supporting SCUDEM, which is a differential equations modeling competition. I will actually drop this link in the chat for you to have available, and feel free to browse through. So MathWorks is supporting SCUDEM. In that link, you will find some useful information on what the competition is about and how to participate. The reason why I'm sharing this is because this was basically the primary motivating factor for us to hold this webinar. We wanted to, because we are providing support and free software licenses to all the participants of the competition, we thought it's a good idea to hold the webinar and basically open it up to, to everyone. One more thing, if you click on this link right here, which says free copy of MATLAB, you will be navigated to this page, this is a MathWorks web page, and this is where you will be able to request a free license if you're participating in the competition. That is, you might already have a free license through your university or your institution or your organization already. With that, actually, let me just show you. If you click request software, just for those of you that will go through this process, you will get this pop-up message, and then if you click on software request form, you will be navigated to this page where you will be asked to enter some basic information about yourself, contact information, company, university name, and so on and so forth. Make sure you're not a robot, because that's a thing these days, and then submit. From there, you will receive instructions on how you can activate your license. Okay? All right, so now that we have that out of the way, we can actually continue on with the webinar. And we're going to talk about differential equations modeling, or you can say mathematical modeling with MATLAB. And the problem, I am getting some feedback from someone, but I think now we're good. Someone might have to mute their microphone, just putting it out there. All right, so the problem we are going to look into today, it's a fairly simple problem, and if you like cats, you are in luck. I mean, who doesn't like cats, right? And worst case scenario, you're like me, I like dogs a little bit more than cats. So the problem we'll look into is, you can see the image on your screen, and on the screen, we have one pair of unspayed cats, which basically means we have two female cats that are able to reproduce. And the question is, if they start doing so, if they start reproducing, can these two cats and their offspring reach the population of 420,000 in 7 years? And the nice thing about mathematical modeling, or mathematical logic in general, is that you can try and make sense out of every random statement you will hear. And of course, this is not random. You will actually see there's a couple of links in this slide that there is some literature around this. But we are going to study the statement, analyze the statement, and basically conclude whether or not this is possible. And I think now is a very good time. Actually, forgot to do that. I will share a folder with you. Sorry, give me 1 second here. This is a MATLAB Drive folder where you will be able to find all the material. So I'm going to copy this link. I'm also going to put this in the chat. Make sure you save this link somewhere if you want access to all the material, the presentation, and the MATLAB code, the MATLAB notebooks we are going to use. You might have to activate your license and create an account before you have access to this folder. Just letting you know. Now we are ready to continue on. All right. So this is the problem we're going to look at. And the approach we are going to follow is this kind of V-shaped workflow. We've already defined the purpose, what we are trying to do with the problem statement from the previous slide. And specifically with MATLAB and with computation, we are going to study design, implementation, test, and evaluation. Okay, this is a cycle we are going to go through, where essentially what we will do is we will start with a model. Okay, whatever model that is, we're going to make an educated guess, or any model what we think might help us get closer to the answer. Implement, test it, make sure it reflects realistic data. It's a practical scenario that we can actually work with, and go back to design, improve, test, go back to design, improve, test. We're going to follow this workflow for the remainder of this webinar. Okay, so this is so if we know nothing, we don't know where to start. This is a very good place to start with this problem. We're studying basically population dynamics, and we have an initial population of the cats, and we want to see what is going to happen over time. And so I'm not going to say, a simple approach, a simple way to start is, go with a model that says, what, the new population is going to be the previous population plus a discrete growth rate or an evolution over a certain period of time. Okay, and this is the discrete growth model we can use to begin with. Of course, there's no MATLAB involved for now, but this is, if you look at the literature or search over the internet, you will be able to find a solid place where to start. And so this is it for us, for this particular problem. You can see the update equation, and we will shortly implement that in MATLAB. Okay, we will do that. Now, bear in mind, there is, because you will see in this slide, there is terms like a discrete population growth rate. What even is that, and how do we determine that, right? This appears to be an important parameter for this model. How do I know? How do I make sure that this is an actual number that makes sense? Well, there is always literature we can look at, and this is one particular paper that we found that explains, reproductive performance in cat colonies over a 10-year period, which is more than enough because we're interested in 7 years. And there are some numbers there, and the numbers there are liters per year per cat, which is 2.5, kittens per liter, 3.6 to 4.2, and this is also important. The female population is about half of the entire cat population. So these are some parameters we are going to make use of. One thing I want to clarify here, because I don't know if English is your native language. Mine, it's not for me. So I had to look it up. The difference between litter and kitten. Okay. So litter is a group of young animals born to another animal, in this particular case, a cat, at one time, while kitten is a young animal, a young cat. Okay. So, for example, we can say a litter of 5 kittens. Uh, all right. That's all we need. Yep. No, we don't go there for now. So that's all we need to begin with. Now I'm gonna move over to the MATLAB drive. And by the way, over here, you're going to see this folder, differential equations webinar. If you double click on it, you're going to see all the files we will use. This is the presentation I just showed you, the slide deck. We have 3 MATLAB notebooks that we are going to cover, and then 1 Excel sheet that presents some data that we're also going to make use of. Okay, so if you click on any one MATLAB notebook, it has the extension MLX. That's how you will be able to identify. You can actually open it up right here on top, open in MATLAB, either open in a desktop version of MATLAB or MATLAB Online. MATLAB Online is actually free. It's free for 20 hours for everyone. But if you have a license, you have unlimited access to both. I am going to use MATLAB Online. It's a little bit more straightforward. I don't think it's a little bit faster than the desktop version. But anyway, so this is the first MATLAB notebook that we're going to use. It's CATS Part 1. And when I say notebook, we call this a live script. It's basically an interactive notebook where you can combine equations, code, images, plots, basically whatever you want. And it's a nice place if you want to have everything, include everything if you're going to submit a solution to a student competition, for example. Okay, you could submit your solution in a notebook if you so wish, or a live script, a MATLAB live script. Okay, so let's look at the problem we just defined and we just started to go over, right? This is the discrete population model that I showed you before. We have a population Pn and an update equation. And using the numbers from the literature, from the paper that I just presented, we are slowly going to start to defining these parameters. And we do so, this is the code. Again, feel free to play with it after this webinar. You have access to every notebook. We start defining these parameters: liters per year, kittens per liter, and percent females. And that's how we're going to calculate this discrete growth rate. One thing I want to point out here is that, as you can see, there is a slider here, so you can actually move this thing. It's not static. You can have the number be static. There is no problem with it. It's just that this gives you a little bit more interactivity and a little bit more testing room. And the way you do this is from up top, you go to the control drop-down menu, and there is a bunch of options for you. The one you choose for a numeric slider is it's a slider, and you can have that be part of your script. All right, so the rest up here, model parameters, we're just defining, the initial model and the problem statement, essentially. P0 is the starting population. We have 2 cats, right, to begin with. A number of years we are interested in testing this model. is 7. So let's move on. Here is where we calculate the population update. And this is the equation that we are interested in. This is where we calculate the cat growth rate. And how we do that is basically multiply the percentage of females times the litters per year per female cat times the kittens per litter, which kind of makes sense, right? If we apply some simple logic. As soon as we have the RD, the growth rate, we can update the population, which is P. P, just as a reminder, we start with P equals P0 up top, which is 2. And then we update given this equation. And this is a simple implementation of the discrete model we saw before. Moving on, we're going to look at some solution arrays. We're just creating some rows here with well, first the number of years. You can see it right here, 0 to 7. And then the population for each year, since this is a discrete case. The starting population is 2. So that's what is happening here. And as soon as we have these solutions arrays, we're going to use a for loop, which is what is going on here, to plot, to visualize the model, the values, the population values for years 1 to 7. Okay, we use the update equation, which we defined before, and then plot the results. So for that, we're going to use the plot function. And one thing I haven't mentioned, I will mention it now, is wherever you see something that you don't understand the syntax of in this notebook, in this script, you can just click on it, right click, help on XY function, in this particular case plot, and you are going to get a pop-up menu that will explain the syntax and every background information that you need to have to use that function. You can either do that or Google the function, you know, in any search engine. You're gonna get the same results. All right, so we plot the results. This is what we get, okay? And you know, from a first glance at this, it kind of makes sense that yeah, we could probably reach the population of 420,000 in 7 years, right? 4.5 times 10 to the power of 5, that's 450,000. That's probably possible. It looks like it. Well, yes, is the initial answer is yes, but there is no upper limit to this. There's no limitation. It's a simple discrete growth model, and there's no upper limit. So this population keeps, you know, increasing and increasing. Which that part is not a very realistic scenario, and we haven't, you know, compared to real data for cat colonies. We haven't done any of that. We just was an initial model, a starting model, which is good enough to begin with, but there is room for improvements. And this is actually the main part of, you know, where math modeling and a couple of apps in MATLAB can make your life a lot easier. So let's move on to the second script, cats part 2. And as the V-shaped framework shows, here we're going to test and evaluate based on real life examples for cat population dynamics. Over here, this first part, we basically plot the previous model, nothing new here, same parameters, and we just plot the cat population. The one quick note that is it's useful is, we have a discrete model that we started with. How does it compare to a continuous model? And you can kind of see over here, if you look at this plot, it has like this exponential uh, growth. So, and if you look at the literature, like studying the literature, studying what information is out there is really important when we are designing a mathematical model for everything, because that will help us inform and improve our model choice. The equivalent differential equation that for that uh, discrete model is highlighted here. Okay, it's a simple differential equation for which the solution is the exponential, of course, right, based on the plot that we saw before. Again, this is all known. I'm not going to go too much into this, too many details. And there is, with some massaging and some algebraic manipulation, we can actually determine what is the connection between the discrete growth rate and the continuous growth rate, because there is an equation for that, and it's highlighted right here. So once we have that, we can actually plot the discrete and the continuous solution to the model together. And this is what this code is about. We're defining a time parameter first that's needed, and then we're plotting the function, the exponential, the continuous function, plus the model that we created before, the discrete model. Again, we use the plot function for both. And this is what we get, right? No surprises. One is discrete, one is continuous. The model is the same. I'm just putting it out there because some of you might want to try a few things with a continuous model and not a discrete model. All right, so this is the juice, the main body of testing. How does my model that I came up with compare to data? And if you go to the MATLAB drive, this is the file that I mentioned before. There is an Excel sheet here with some cat population data, and this is what we are importing with this line of code right here. We're importing. It looks like this. You can see basically what it looks like. It's like a 2-year. No, it doesn't show very well here, but I don't know why. Oh, interesting. Anyway, there is cat population numbers for 24 months, for 2 years. Okay, so we can get an idea of what uh, could what real data could look like, and so we will try and test our model with this data. So we have the data, we import the data in MATLAB. We have our parameters. I guess we redefine the parameters here. Again, with some sliders, we can adjust this. It just provides a little bit of room for testing, some variability in my modeling choice. That's all that does. We initialize the parameters, starting cat population, number of years. We convert, in this particular case, I think we're using a continuous model. Yes, we convert to a continuous model. Okay, using a conversion between discrete and continuous that we had before, and plot the results. We plot the results using the plot function, same as before. And this is the output. Now, blue circles are the data. The red continuous line is my model. And it's not the best, it is something. Now, keep in mind, if you actually change some of these numbers, so let's say I come over here and I modify kittens per liter, change that, sorry, I have to rerun this, run the script again. I don't know why this error occurs. Huh, that's interesting. I haven't seen this before. Give me 1 second here. I'm gonna reopen this in my MATLAB online because this has never happened before. All right, right. There you go. I don't know what happened there, but it's all right. So we changed some numbers, and you can see that the graph, the continuous line, is actually way off now. And the more you tweak these numbers, actually, let's change that a little bit more so you can see it. You can see the difference, right? It's getting way off and way off. So you can manually change that and see what um, um, model fits best, but it would be way easier for this to be an automated process. And this is what we will do next, because there is no way for you to optimize this manually unless you do either some really advanced mathematics or you just like do very extensive testing. Now, the way we automate this is that's where curve fitting toolbox is going to come into play. There is two options to use here. You can either use the, if you like, a programmatic approach. I don't in this case, but I'm gonna, just for the sake of completeness, there is the fit function that you can use. So make sure that you come up with the optimal model that fits the data that you are importing into MATLAB. The data that we imported through our Excel file. Again, as a reminder, okay? The reason why I don't like this is because if you use the programmatic approach, you also need to specify what model you want MATLAB to try and fit the data to. You can see right here, I'm using the exponential model. Well, because I know that this is most likely, well, it's not, but anyway, I know that exponential might be a good choice. But, a practical question can be, okay, but how do you know? How can you know that one model will be better than another? So you can do that, but what I recommend you do is you go up top in the apps tab, and we have to open up curve fitter. It shows up in my selection because I've been using it a lot to prepare for this webinar. But if it doesn't, if you click on the drop down menu, there is a bunch of apps you can use in MATLAB. In the math, statistics, and optimization category, you will find curve fitter, and you can favorite it if you want to have easy access to it. Anyway, we'll click on curve fitter. Give it a second to start. This is the curve fitter app, and the first thing we do here is select our data. Okay, so if we click select data, we're gonna get this pop-up menu, and we are going to have to select X and Y data. So X data, by the way, this is all related to how you imported your Excel file and what are the columns and the rows, and all that. So you will know once you see this pop-up menu, you will know what you have to select to get the correct values for X and Y. So I know here because if we look at the data right here, You can see data month, data population. So that's why I select, oops, where is it? No. Over here, data, and then from the data Excel file, I select month. That's my X. And then for Y, data and population. And we're going to get the same plot as before. This is the same plot as before, no changes. We can now close this. So once we have this, you can actually select any function that you want to fit into the data and have MATLAB automatically optimize the parameters of the model that you are trying to fit to. Okay? And this is just so useful for so many reasons. You can either use it for, for your initial model, and you can also use it to test if your final model makes sense and it's optimal. There is a drop-down menu where you can select polynomial functions, exponential, logarithmic, Fourier series, sum of trigonometric functions. You can even define your own custom equation if you want to be, overly creative. So you have many options here, and you can see, like, for example, let's go with exponential. Select exponential, MATLAB automatically optimizes the function and gives you the values, you see right here. This is the function, exponential of curve fit. F of x is a times exponential b times x, and gives you the values of a and b with a lower and upper limit as a confidence bound. One more thing I want to show you for the curve for the curve fitter is that if you, let's say, for example, I select the polynomial fit, okay? You can select the degree. Degree right now is 1, which means that it's a straight line. You can also check the root mean squared error. By the way, the curve fitter uses least squares to calculate the parameters, just so you know. You can see the root mean square error is 4.3. And as you start increasing the dimension or the degree of the polynomial, right? 4, go to 5, go to 6. You can first of all, you can see that it's a much better fit, and you can see the root mean square error going down and down, further down. So you can check a variety of models and pick the best that fits your data, or any real data that you have that you can associate with a modeling problem you're trying to solve. Okay, that would be all for the curve fitter. So I'm just gonna close this now. Let's not save this. And let's continue from where we were. So, all right. Yeah, that's about it for the second notebook. And now we move on to the third and final notebook. And that's where we will make the final, touch, final improvements on our model. Because one thing we have not considered, there is this thing in population dynamics for any species, really, that is called the carrying capacity. And so what this thing essentially is, it's a maximum population of any species that an environment can sustain. For cats, for example, it can be determined by factors such as resources, food, water, shelter, so on and so forth. Because if you recall, we assume that there is no, upper limit, no carrying capacity whatsoever. But realistically, there is. And this is what an improved model, such as the logistic growth model, offers us. again, this is, you have to do some search, some analysis, some investigation online to make sure what literature exists around this problem, what models people are using, and make sure you go with the best option. And from there, you can optimize based on the specifics of the modeling problem you are trying to tackle. So these equations are known, right? You can find them in the literature online. It's the differential equation for the logistic growth is known. That's right here, as well as the solution for the logistic growth model. And for this particular case, again, we're doing the same thing as before. We are initializing our model. We are the only difference is we are using a carrying capacity. And for this case, we are using a fixed number, which is equal to 1,000. This is a random choice. It doesn't matter. It's a constant. It's a fixed number. Okay, as a first step. Bear with me. We're gonna improve. We are also going to improve that in a second. Okay, so we define K. We define the solution for the logistic growth differential equation that we saw before, which is basically this. Okay, define that in MATLAB. This is how you do that. And plot the results. So plotting the solution for that looks like this. Okay, this S type function that does not exceed 1,000 cats over the time span of seven years, as expected. Okay, and as designed. Okay, that's good. That's what the carrying capacity does. Now the question is, actually a quick note before we move on to finalize the carrying capacity. The coding moment in this particular notebook, we are trying to show you how you can define function handles in MATLAB, and that's essentially the way to do it. You create an anonymous function. This particular one is a times cosine of x. You just add an at and an x in front of it. The reason why we do this is we will need this to numerically solve an ordinary differential equation and plot the results for our model. Just keep that in mind. Yeah, it's there for you, of course, to look and study. All right. So I'm gonna quickly go back to my slide deck now to show you this. And all this does is just some evidence, some data that goes to show there is a lot going on in this slide, but what matters really is the bold bullet point in the bottom half, which states that human population is correlated with community cat population. And this evidence in particular is coming from Auckland in New Zealand, but there is data that supports that. And it's actually not surprising because if you think about it, all the limiting factors that determine a carrying capacity of a population, shelter, water, food, and so on, are taken care of for cats if we consider that they live with humans, right? Because we take care of them. So there has to be a correlation between the two. So the question is, how can we incorporate this information into our model? And that's the final task that we are going to add to our previous script. Let me go back to my to our notebook here. This is what is happening here. So based on the data, actually, one more thing, we're gonna need this slide as well. So before we jump into the notebook, this is the logistic growth model modified to add a time varying carrying capacity that is proportional to the human population. Okay, K of t equals A times H of t. That's what modifies the carrying capacity to be dependent on the human population. And depending on what part of the world we are testing this model on, in this particular case Auckland, we can derive the value of alpha. And based on the data that we saw before, alpha is can be defined, can be derived as 158 over 10,000. And we also need H of t. H of t is basically the a linear approximation of the Auckland population. It's nothing. There's nothing really very complex about it. It's like 900,000 was the initial population that we assume, and then a 20,000 increase year over year. Okay, that's that. So all of this we are going to incorporate into our model now. So now we can go back to our notebook. Yeah, and essentially what we do is we define all these equations, all these parameters in this box. Okay, H0, initial population in Auckland, it's 900,000. We have the population increase rate, which is 20,000. We have the alpha parameter, which is the proportionality constant of the cat population, of the carrying capacity to the human population in Auckland. And then number of years. Here we specify 20. It's okay. We can say 7. 20 just gives us a better view of the cat population over time. It's fine. So the reason why we mentioned the function handles before is because we now have to solve the differential equation. Okay, we have to solve to plot the results and see what happens over time. And for that, we have two options. In the notebook, we cover the numerical option, solve an ordinary differential equation numerically. This is where we define the differential equation right here, okay, using function handles that's listed, that's mentioned before, and then using the ODE solver ODE 45, which again, there is a lot of documentation around this, and there is a lot of information. Right click on it, help on ODE 45. You're gonna see syntax, when to use it. Yeah, a lot of information. Relevant examples, more documentation. That's there for you. It's available. And the thing with numerical solution of ODE is that it's always reliable. Well, almost always. But because the thing is, you could be creative with the model that you choose. And so it might be the case that you're not able to solve it analytically. Now, if you can solve it analytically, we also have, of course, a documentation page that I'm not going to cover. I'll just put it in the chat that covers that in detail. There you go. That's in the chat. That covers the analytical solution of an ordinary differential equation. But in some cases, it might not work. Okay, so you have both options available to you. All right, now the final step, plot the results. We define the model, we modified it with the carrying capacity, plot the results. Again, we use the plot function for that, add some labels, and this is what we get. The red dashed line that we plot is basically K of t. So we plot that to just to make it obvious that the population will not go over the carrying capacity, right? Again, as designed. It's just that in this case, the carrying capacity is a line. It's not a constant number, 1,000, which we used before. Yeah. So this gets pretty close to reality, okay, based on real data. And I guess since we started with a question, and the question was, can two cats reach the population of 420,000 in 7 years? In this particular case, for Auckland, it doesn't look like it, right? 7 is right about here. And you can see we're getting close to 1.5 times 10 to the power of 4. That's not even close to 420,000. But again, and here is when you can play with the numbers, do some testing on your own. You know, one very important number here is number alpha, which defines how much humans like cats and how many of them decide to adopt them and take care of them. So for the case of Auckland is 158. If there are places in the world where, you know, I can add a 4 in front of this number, people like cats so much that, you know, the number gets so much bigger, that much bigger, and run this again, you will see that in fact it it is possible. So I guess our final answer here is it all depends on alpha, and it all depends on what how the carrying capacity allows humans or tells us that humans uh, are much more likely to adopt cats in that specific part of the world. So it depends on which part of the world we're talking about, essentially. That was it for today. That's all I had. So we saw how you can use the curve fitting toolbox to optimize your model and how you can solve and plot differential equations for any mathematical model that you choose. Yeah, we can close. Thank you very much all for attending. We can now, I will stop the recording.